Hello everyone. Welcome to the Space City Design course. In this class, we will mainly focus on the design of the Operation and Maintenance Department. We will discuss two main topics: the quantitative estimation of the Space City's electricity consumption and the qualitative analysis of the Space City's water recycling system. The operation and maintenance of a space city involve many complex systems. Among these, the power supply system and the life support system are particularly important. The power supply system must meet the various power demands of the city, while the life support system is responsible for ensuring the basic living conditions of the residents, including the recycling and use of air, water, and food. In the unique space environment of space, managing and planning power consumption is crucial. We need to clarify the power requirements of different functional areas and equipment to ensure the smooth running of city activities. At the same time, we also need to consider the sustainable supply of energy and have enough reserves for emergency. Chapter 3 of the RFP clearly requires us to estimate the space city's power supply system. The city depends on electricity for everything, like basic operations, life support systems, industrial production, and food production all require sufficient power. In emergencies, the city must also have the ability to reserve energy to maintain its operation at the minimum power for at least 100 days. The complex issue of designing the power supply system can be broken down into simpler problems, such as calculating the power demand for industry, agriculture, residential areas, and energy storage. Next, we will look at how to estimate and understand the power consumption, power generation, and energy storage in detail. Let's start by estimating the electricity consumption for industrial use. The space city we are designing will be part of an industrial complex connected to the lunar base. The lunar base will handle mining, while the space city will carry out smelting operations. To estimate the power demand for industry, we can make the following two assumptions. First, the power consumption of factories on Earth and in the space city is similar under the same production output. Second, both use similar production technologies and equipment, ignoring environmental differences. Taking the example of mining the lunar mineral resource ilmenite, we can assume that the space city's industry is based on steelmaking. To estimate the power needed, we can search for the power consumption of steel mills on Earth. This data is easily available online. When it comes to agriculture, things get a bit more complicated. We can start by estimating the basic caloric needs of everyone living in the space city. The daily calorie intake per person can be easily found on the World Health Organization's website. Once we know the total caloric requirement, we can calculate the amount of agricultural products needed based on a balanced intake of protein, fat, and carbohydrates. We can make some reasonable assumptions here. For example, we assume that only 5% of the light energy is converted into usable plant biomass, roots, stems, leaves, and fruits. Additionally, only 10% of the entire plant is edible, and the remaining 90% could potentially be converted into electrical energy with 30% efficiency as biomass energy. If we need to consume animal protein, we can assume that animals in the food chain have about 10% efficiency in converting energy. Using these assumptions, we can estimate the total amount of artificial light energy required for agricultural production. The power consumption for water, fertilizer, and facilities can either be ignored or factored in with a coefficient. There is also a certain loss when converting electricity to light, but we assume that new technology could achieve 50% conversion efficiency. Combining all of these factors, we can calculate the total power consumption for agriculture. Of course, we can also look at data from Earth, such as the power consumption of vertical farms, and use that as a basis for estimating the agriculture power needs for the space city. The assumptions we've made so far are just estimates. Accuracy is not the focus here. What is important is understanding the approach to these calculations and knowing how to come up with reasonable estimates. To simplify the problem, let's assume that the space city consists of agricultural, industrial, and residential areas. We can estimate the volume of the residential area of the space city and then compare it with similar enclosed environments, such as the International Space Station, the Tiangong Space Station, or even nuclear submarines. Simply assuming that power consumption increases proportionally with the size of the space might lead to an overestimate. We can reasonably assume that, Because of the economies of scale, the efficiency of the entire system can improve by more than 10 times, meaning the power consumption could be only 10% of that of the International Space Station for the same volume. Now that we have a basic understanding of the power consumption, we can turn to power generation. We need to consider several factors. Where is our space city located? In the Earth-Moon space, the solar energy density is approximately 1,300 watts per square meter. If we use solar power, we need to consider the efficiency of the conversion efficiency, which could be around 40%. Since our solar panels cannot always be perpendicular to the sun's rays, we might lose about 50% of energy. After considering all the above factors, we can estimate the total power generation needed. Then we can estimate the number and area of solar panels and work with the structure design team to determine the best way to deploy them in the space city. Another important factor is the redundancy of the SIST, which ensures that backup power is available when needed. Estimating energy storage is relatively simple. First, we need to determine which functions must continue in an emergency, like the life support system and agricultural production. Industrial activities may be stopped in an emergency. Based on this, we can calculate how much energy storage is needed to maintain these essential functions for 100 days. In addition to the aspects mentioned above, we also need to consider power consumption for managing atmosphere, water, and waste streams, as well as spaceport cargo handling and aircraft fuel. We can use similar estimation methods for these as well. Finally, we will present the power consumption analysis of each part in a table, making sure the units are consistent in kilowatts. In the design of a space city, several key principles must be followed. The rationale. The design is based on reasonable assumptions and reliable data, forming its foundation. Feasibility. The design must align with scientific laws and engineering principles. Efficiency. The goal is to optimize resource use, such as energy and material efficiency. Consistency. Coordination with other departments is crucial to ensure smooth operation across all systems. Safety. Redundant designs are needed to ensure the safety of the city and its residents. In the harsh environment of space, the space city first must to ensure the survival needs of the city's residents. That is, it requires a life support system. The life support system covers multiple aspects such as oxygen, food, water, and environmental control. Appropriate air composition and pressure conditions are the primary conditions for survival. Food includes both plant and animal. Water is needed for drinking, sanitation, and air humidity regulation. Environmental control is responsible for the purification of air and water, waste management, such as urine, feces, carbon dioxide, sweat, etc. In the space city, most materials need to be recycled to reduce dependence on external resources. Because resupply from Earth is costly and infrequent, let's take the valuable water resources of the space city as an example to explain in detail how to conduct a qualitative analysis of the material cycles in the space city. The space city must maximize the efficiency of its water recycling system. Every drop of wastewater, whether from human activities, plant cultivation, or industrial production, must be collected, treated, and reused. In addition to wastewater, water vapor condensation and some other sources must also be considered. The water cycle system does not exist in isolation. It must be well integrated with other life support systems. Processes such as plant transpiration and hydrogen combustion also produce water, and electrolysis of water can generate oxygen. These processes are interconnected, forming a complex water cycle system. When we submit the Space City design proposal, the water cycle part should be presented as a flowchart. This chart will show the water's journey from human urine and respiration through condensation, electrolysis, distillation, and disinfection and into recycling for the agricultural irrigation and industrial use. You just need to understand the water cycles in your Space City design and find reliable literature to support your theory. The specific flowchart may vary slightly, but the overall process will be similar. In Space City design, qualitative analysis and quantitative calculation work together. Qualitative analysis help us understand the basic principles, relationships, and factors at play, while quantitative calculation provide precise data to ensure that each part of the space city functions properly. In today's digital age, AI tools can greatly enhance our work efficiency. We can also use AI to generate ideas and inspiration for space city designs, search for data on space environments and exploration technologies, and even create preliminary concept sketches to improve design efficiency and creativity. However, we must define clear boundaries for AI use. AI should not be used to directly generate a complete design proposal, write the core content, or conclusion. The design details of key structures and complex systems should not be fully generated by AI, as these outputs may not ensure the scientific accuracy, reliability, and innovation of the design. Today, we focused on the quantitative estimation of power consumption and the qualitative analysis of the water cycle in Space City's operation and maintenance department. It is important to grasp the significance of these concepts and apply them effectively in the future design work. Additionally, we should use AI tools properly, leveraging their supportive role without over-relying on them. Okay, that's all for today. See you next time.